Assalamu alaikum wa rahmatullah, and good afternoon to all of you, our respected viewers of the Voice of the Cape's Facebook page, as well as the VOC's YouTube page. It gives me great honor and pleasure once again to introduce Brother Imaad Isaacs from Futures Academy SA Online High School. And of course, this is the annual Matric Revision program that Futures Academy has in collaboration with the Voice of the Cape. Today, inshallah, today's session will be dedicated to all of the mathematics students out there. And Brother Imaad Isaacs will be going through mathematics content for paper one, inshallah. This is, of course, the main time of the year, the most important time in any matriculant's life. We are going to have to embark upon the NSC examinations, and we hope that each and everyone is preparing well for this up and coming period, inshallah. Without further ado, we call upon Brother Imaad Isaacs to conduct today's session on the mathematics revision for paper one, inshallah. Bismillah.
Okay, assalamu alaikum wa rahmatullah, and welcome. It's been a week or maybe 2 or 3 weeks since our last revision session. So today we want to continue. I think we've covered quite a bit on functions. I'm not sure if we had to have another session on functions, but we'll definitely revisit parts of that as we go through the section of calculus and also some of the other topics, right? But yes, when we look at paper one, we're coming towards wrapping up the bulk of it. We've covered algebra, we've covered functions. Sequences and series is really just applying the things that you know already from algebra. It's just mostly direct application of the formulae, okay? Now, we touched on functions. We went into quite a bit of detail with regards to transformations, the format of the functions, adjusting the various parameters, and then we also dealt with some of the basic questions that we look at over there. Today, we want to move on. We want to tackle the next big section, which is also between 35 to about 40 or 50 marks in your paper, right? And that's going to be calculus. So that's really the focus of today, right? So let's put it up there, calculus. Hey, that font looks cool. Okay, so that's what we're going to be focusing on today, calculus. And now, when we talk about calculus, for me, it's always critically important to see what goes on in that section. What are the various things that we actually need to know about? Now, had I been in a revision class, I'd probably ask you, the students, to tell us what are the things that you know that relates to calculus. Okay, so let's see if we can make a list. Let's make a list. What goes on in this section? Okay, one of the first things you learn about in calculus is limits, right? Then you also learn about things like the average gradient, right? Let's think. Average gradient, limits. You learn about differentiation. Okay, 2 ways of dealing with differentiation. One is through rules and one is through first principles. And we'll talk about what each of those are. Now, remember, again, this is a revision session. So the idea here is we want to quickly get an idea of what the topic entails when we look at a few exam questions and kind of crash course certain parts of this, okay? For an in-depth understanding, visit the YouTube channel. I think there's videos I made somewhere in 2015 or 2016 where we cover each of these topics in the calculus section across about 36 or 38 2 to 5 minute videos where all of these are done in detail. So things like limits, we look at graphical interpretation of the limits, which is not examinable, but it's critically important for you to actually have that understanding. Now, in a revision session, of course, we don't really have all the time to go through that, and that's why we're crash coursing it, okay? So we've got limits, we've got the average gradient, we look at differentiation, rules, and first principles, and then all of these things come together when we are sketching graphs, okay? So when we are sketching graphs. So I would say that really sketching graphs is kind of our aim here, and also interpreting things from the graph, and to get to that, we're going to deal with limits, we're going to deal with differentiation. But anyway, let's see, what else? You can use all of those things to sketch a cubic graph, right? That is a specific polynomial that we're looking at. Then you can also get questions where we are given the graph and we have to interpret certain parameters, we have to find the equation. So let's make that another thing that's important, finding equations and understanding the rate of change, right? Which is just, instantaneous rates of change. And we'll also look at optimization. So that's really an overview of everything that there is in calculus. Okay. Limits, average gradient, differentiation rules from first principles, and the rules, and then we look at sketching graphs. So today what I really want to do is I want to talk about two things. I want to touch on, or maybe the first three, limits and differentiation rules. And if there's time, we can briefly talk about the average gradient and how to find that. And that's really nothing fancy because you've seen it since grade 9, okay? It's just now listed as a specific concept. Okay, so let's go to limits. What is a limit, right? Now, when we talk about functions, it's very difficult to do this without graphically examining it. Okay, so if we talk about a limit, right, and I take a function, and let's say that function looks like this. That function looks like this, okay? Then I can say that there are certain values on the x-axis here that correspond to, let's say that's going to be 4, and on the y-axis, this corresponds to, say, I don't know, let's make it 8. Okay. Now, when we call this, let's give this function a name as well, and we'll call this function f, right? So, and this is the x-axis, this is the y-axis, and so we will say that y is equal to f of x, okay? So that functional values often refer, and of course, not often, but they refer to the y values. And if they refer to the y values, then we can consider that the name I've given is just y is equal to f of x, where f is the function notation, something we've covered previously, and x over here just tells us what is the independent variable. So f is the function, and it outputs a y value, and y depends on x. Okay, so those are things that we know. Now, when we speak of a limit, and if I ask you to tell me what is the limit as x approaches 4, okay, usually we look at partial limits and we say x approaches 4, right, for the function f of x from the left-hand side. That's what that little negative means. All that means is if I were to run on this graph, take your fingers, let it do the walking, and it's running on this graph, run, 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 run. As I run towards 4 from the left-hand side, what does the function tend towards? Well, the function tends towards 8, okay? And that's the answer. That's known as the left-hand side limit. Now, generally, most grade 12 textbooks don't tackle these in terms of the partial limits or in terms of left-hand and right-hand side limits, because we just expect you to follow a certain mechanical procedure to get the answer. And that's what I'm going to do with you today. But before we kick that off, we want to understand this, right? If I say x approaches 4 with a plus over here, that simply means that I'm running on the graph towards 4 in terms of the x, and where do I end up in terms of the y? Well, I also approach the number 8. And so here I say the left-hand side limit, which is this, and the right-hand side limit are equivalent. And if they are equivalent, we can say the limit exists, right? And that's written as limit as x approaches 4 for the function f of x, and that's equal to 8, right? Now, I'm saying when the left-hand side limit is equal to the right-hand side limit, the limit exists. What does that mean? It means that there's also a possibility you can get a case where the left-hand side limit does not equal the right-hand side limit. But all of that is beyond the scope of the curriculum. Okay, so let us continue. Our focus right now is to look at limits. Okay, so another thing I want to mention to you very quickly, this function that you see over here is what's known as a continuous function. Okay, there are no gaps or breaks along the way in terms of this function. That's why it's a continuous function. Okay, it's a continuous function. Now, how do you evaluate limits in grade 12? Let's make a note of that. That's really what we want to do, and that's what we want to look at. Okay. Evaluating limits. Right. Now, in grade 12, we use a method that we will call plug and chug. Right? That's what we're going to call it. Now, you can't just use plug and chug with anything. Plug and chug as a method involves substituting. And to utilize a plug and chug method, we must have a continuous function. So generally the functions that they give you in Matric are all continuous, and you will use a plug and chug method. Okay, so how are we going to do that? Right, let's give you an example. What does it look like? Right, let's specify this. we're going to say, let's look at the example of the limit as x approaches a, right? And what is a? A is some constant over here for a function f of x. Now remember, f is just a name to keep track of the functions here in function notation. Could have been q of x, p of x, t of x, but f of x we have, okay? And we're being specific in terms of how we want to define this, right? And I'll say is equal to L, right? Okay. Now, what does this mean? This limit is the value, this L, right? The value, this limit here, this entire limit is this value as we run towards a particular value of a certain function, right? So what does this mean? This limit here, the entire limit. Okay. Let me be specific. This value, right, or the limit, this value. No. Guys, forgive me here. This limit, right? Okay. Why am I doing that? Clearly, I cannot compete with the font. So let's list it here. This limit is the value, right? That, in other words, a number, the value that, right? F of x approaches, okay? In this particular case, it's L, right? As x approaches a, as x approaches a. All right. So if we go back to the example, we could see that the limit itself is equal to 8, right? So in other words, the limit's value is 8, which is the functional value that the function tends towards or approaches as the x moves closer and closer to 4, right? Okay. So another way to evaluate this, if you go back to what we discussed when we spoke about functions, right? Here, there's a graphical representation of the function. So if I just look at 4 and I run towards 4 from both sides, I see where do I end up in terms of y. That's 8. That's our limit. Now, if this curve that we have over here had an equation or an expression, or if it was expressed algebraically, then the value that you find for this 8 can simply be given by substituting the 4 into the f, right? That's something you know. Now, to go back to this over here, we want to teach you how to handle this. Again, if this isn't too clear right now, you can always rewind, review, and go back to this video. But let's teach you how to do it, because I think that's the important part. Okay, calculating limits. At grade 12 level, so these are tricks, right? At grade 12 level, the first thing you want to do is you want to substitute, right? You substitute directly. That's your first step. Now, after you substitute in step 1, one of 3 things will happen for the questions that we get. Number 1 is that you get a value, right? That means that the answer is real. So you get a real number, okay? That's type 1. The second option is type 2, the limit does not exist, right? In other words, you get an answer of infinity, or you get undefined, or you get the limit does not exist. Okay. And the third option that you can get is what's known as an indeterminate form. So an indeterminate form, I'm going to note it over there, indeterminate. An indeterminate form is a form of 0 over 0. Now, if you get an indeterminate form, you're not done, right? You need to do a secondary step. And that secondary step is you are going to factorize, right? There we go. You're going to, second step, you're going to factorize, right? And then simplify. And then you will substitute again. Okay. So let's look at examples. I'm going to keep that part on the screen, and let's see. Let's keep that part on the screen and just put it in the corner over there, because that's what we want to do. We want to use the plug and chug method. And then we want to, okay, we want to look at a few examples. Okay. Now, there is a special case where this doesn't really happen. Okay. That special case is if the function we are given is a constant, right? So let's list the special case here. Special case. And that special case is the limit as x approaches some number, and remember a is just a placeholder of c, right? And c is a constant. Now the limit of this thing is just equal to c, because in other words, this does not depend on x, right? So obviously we can't evaluate it. Okay, so let's go to plug and chug. Plug and chug simply means to substitute directly. So let's look at a few examples quickly, right? Let's take the limit. Let's just take functions, right? So I give you a limit, and I say x approaches 2 of the function x plus 6. Okay. So what you're going to do when you're evaluating this limit, you plug and chug into the variable. So the limit here is 2 plus 6, and the answer is 8. So since I got a real number, this is an example of case 1. Okay. The first case, that's the second case, and this is the third type. Okay. Now, let's look at another example. Another example is if I have x plus 6, right? Let's take x plus 6, and let's make it the limit of a function as x approaches 2 of x plus 6 all over x minus 2, right? So let's see, if I substitute into that function, what do I get? I'm going to get in the numerator 2 plus 6 over 2 minus 2. And so clearly I have 2 plus 6, and that's going to be 8 over 0. This is going to give me what? Right? 8 over 0 tends towards infinity, okay? So remember, division by 0 is always undefined. And here we can see the answer here is undefined, okay? Now, in this particular case, that's an example where the limit does not exist, right? This is an example of type 2 because I've got 0 in the denominator. And something over 0, which is not 0 on top, that is infinity, right? It tends towards infinity. So this is an example. The answer to this question here, if you were told, evaluate this limit, it's going to be it's undefined, or therefore the limit does not exist. Okay, let's turn the same one around just to get an idea of this example. If I take the limit as x approaches 2 of x minus 2 all over x plus 6, that's going to equal to 2 minus 2 over 2 plus 6, and that's going to equal to 0 over 8. Now, remember, 0 divided by any number that is not 0 is not an indeterminate form. So 0 divided by anything, the answer is actually 0. In this case, I have a real number, right? So if I have a real number, that thing over there that you see there, that's real. That indicates that the limit exists, right? So the answer to this question is 0, but the answer to this question is actually undefined because we are dividing by 0. Okay, let's move forward. Right, let's look at an example of an indeterminate form. And then I want to do 2 or 3 examples very quickly with you guys. Okay. Indeterminate form, let's factorize something quickly. Let's take the limit, right, as x approaches 2, right, of x minus 2 into x plus 5, x minus 2. X plus No. I'm thinking of actually factorizing it here. So x squared plus 3x minus 10. X squared plus 3x minus 10. Okay. So remember the plug and chug method says the first thing you do whenever you get a question, it asks you to evaluate the limit, and this will work for anything in grade 12, right? Is you are going to substitute directly. So when I substitute in here and I put in 2, 2 squared is going to give me 4. 4 plus 3 times 2 is going to give me 6 minus 10 divided by 2 minus 2. 2 minus 2, that's going to be 0 on top, divided by 0 at the bottom. So we call this an indeterminate form. Okay? So this indeterminate form, ladies and gentlemen, this is not the answer, because the first one, when I plug and I chug, I get an answer. It's real. The second one, I plug and I chug, I got some number over 0. That's actually undefined. Okay? The third example over here, I've plugged and I've chugged, and what do I get? I get 0 over some number, and 0 divided by anything is 0, right? However, in the case of this example over here, 0 over 0, 0 over 0, this is still the example of type 1 over there, right? But in this particular case, this is type 3. It's an indeterminate form. So what do I do? How do I handle it? What do I deal? Okay. How do I deal? Well, I determine that limit by factorizing. So I'm going to say, let's find the limit. And I don't remove these words of limit because I haven't evaluated it yet. I only remove it once I substitute in. So let's factorize this. Factors of 10 I subtract to give me 3. That's going to give me x and x. I've got 5 and I've got 2. And yeah, it's going to be plus 5 minus 2. I've now factorized the numerator. The denominator, I'm sitting with x minus 2. I can put that in a bracket. And now I see that's a common factor. So I simplify that and that falls away. Now this simply gives me the limit as x approaches 2 of x plus 5 now, right? These two things are equivalent. And now once I substitute that 2 into that x over there, right? Once I substitute that 2 into that x over there, I'm going to end up with 2 plus 5, and that's the answer of 7. Once I substitute, I drop the notation indicating limit because now I'm actually evaluating the limit. I'm getting to that answer. And here the answer is 7. Okay, so let's see if we can give you 3 or 4 examples very quickly, and then we're going to move on to the next part where we're going to go to differentiation from the rules. So, candidates, make sure that you have this down, that we quickly have how do we determine limits. We substitute directly. One of 3 things will happen. Either it's going to be indeterminate, or we're going to have a limit that does not exist, or it's going to be a real number. Okay, right. What's the example of the special case? Well, if you're given a question where the function is a constant, right? If the function is a constant, let's say they ask you the limit as x approaches 4 for the function that is 2. You know, if you draw that function is just a horizontal line, because the functional value will just be this. This will be a functional value at 2, right? So here's 4, and when you run on this curve, right, towards 4, it's 2. When you run on the curve towards 4, it's still 2. Even if it was approaching, let's say this is negative 8, right? Even if it was approaching the limit of the function as x approaches negative 8, right? For the function that is 2. And what is the answer? Well, the answer is just 2. And this was the example of the constant case. Okay, now, what can we do? What can we do? Let's give you 5 examples to do very, very quickly. Right? Let me just bring up an example very quickly. Right, let's list this. Examples 1, 2, 3, 4, and 5. Let's evaluate limits. Take the limit as x approaches minus 3 of 3x. Okay, tell me what that answer is. Remember, you must plug and chug. Okay. Then let's take the limit as x approaches 5 of x squared minus 16. Then x squared minus 4 minus 2. The limit as x approaches minus 2 of x squared minus 4 all over 3x. And yeah, let's start with that. Okay, so while you guys are doing that, let's give you 2 minutes to quickly complete that. Okay. And let's put this other one at the bottom. The limit as x approaches 1 of x squared minus 2x minus 3 all over x minus 1. Okay, let's give that a go. Remember, we're going to plug and chug. Okay, let's give you 60 seconds to get started, and then we'll continue. Okay, so let's see if we've all plugged and chugged, and let's give that a go. Okay, so solution over here, this one is fairly simple. I take this negative 3, I substitute it in the x. 3 times minus 3 is minus 9. Here I've got 5, I substitute it in the x, and I drop the limit notation here once I evaluate it. That's going to be 5 squared minus 16. That's going to be 25. 25 minus 16, the answer is 9. What happens over here? That's a minus 2. Okay, so minus 2 all squared. Now, this one looks a little bit interesting. Okay, not really. Minus 2 all squared minus 4 all over 3 times minus 2. And we can calculate and work that out. And when we do, what do we get? What do we get? Minus 2 all squared, that's going to be 4. 4 minus 4 is 0. 0 over 3 times negative 2 is negative 6. 0 divided by some number is still 0. So remember, when 0 is in the numerator, you get an answer. When 0 is in the denominator with something non-zero on top, it's of course undefined, tending towards infinity. Okay, before we come to this one, let's do number 5. Number 5's question has got, if I substitute 1 in here, 1 squared is going to be 1 minus 2 times 1. So that's going to be, let me just check. If this is going to be, yeah, that's going to be minus 2. Minus 2 minus 3 is minus 5. Minus 5 plus 1. Okay, so in this particular case over here, when I substitute 1 in, 1 squared is just 1. That's going to be 1. Minus 2 times 1 is just minus 2. So that's going to be minus 5. 1 minus 5 minus 4 divided by 1 minus 1 is 0, right? So in this case, 0 is in the denominator. That's basically infinity. And here we say that the limit is undefined. Therefore, the limit does not, the limit does not exist. Okay, let's go to this example. So I've thrown that one in there because plug and chug works exactly the same, right? Here we have the limit as x approaches 90 degrees of 2 to the sine x minus 2 to the cos x, okay? But it's the limit as x approaches 90. So to get this limit, you know you must substitute in, plug and chug all the way. That's what we can do in Matric. We can plug and chug. Substitute the 90 degrees into sine x. So 2 to the power of sine of 90 degrees minus 2 to the power of cos of 90 degrees. Okay, so offhand, someone needs to practice, but sine of 90 is 1. Cos graph, cos of 90 degrees is going to be 0. So this is 2 to the power of sine of 90 is 1. Okay, minus 2 to the power of this part over here, cos of 90 is 0, right? And 2 to the power of 1 is simply 1, and 2 to 0, 2 to the power of 0, or anything to the power of 0 is 1. So 2 minus 1, the answer is 1. Okay, so there we've done a few basic examples. We did not see in this particular series of questions an example of the third form where we had 0 over 0 and needed to factorize. But the 0 over 0 example is a very important one. And just remember, start with plugging and chugging and look for the 3 things. Okay, so let's quickly catch our breath, and then we're going to move on to the next part. And for the next part, candidates, I want to talk about the rules of differentiation. And this, we're also going to talk about first principles. Where's my head? It's principles with an E and not an A. Okay. Right, so let us continue. Differentiation. Just trying to get to the bottom of this. Okay, so for differentiation, these are giveaway marks. Okay, differentiation. Differentiation, we're going to do 2 things. What is it really? Right, this is finding the derivative. Okay, now what is the derivative? Hey, I'm not going to use 2 very, very formal definitions. Derivative. What's the derivative? The derivative, right, is the gradient at a point, right, or a single point. Okay, and when we use the rules, then it's like a shortcut for finding the gradient at a point. Okay, so how do you find the derivative? The formal way to do so is known as first principles. And what is first principles? First principles is i.e. using the definition. First principles is using the definition of the derivative. So if the question says, find the derivative of the following using first principles, or find it using the definition, then you're going to apply first principles, generally for about 3 to 4% of a question paper, because it can go up to 6 marks, right? And yeah, 6 marks is 4% of your examination. And this year is really, really giveaway marks. If you're learning it today, you can get all of that. Okay. The other way to do so is using the rules. And the rules will be the shortcut. So in terms of learning this, we're going to start with a shortcut. Okay. Now, the only rule that you really need to know, okay, there are various rules, but at grade 12 level, we only learn one rule, okay? And that rule, the rule that we learn is known as the power rule. Okay. Now, the power rule is a shortcut for finding the derivative, right? Shortcut for finding the derivative, right, of a polynomial function. Okay. Now, what is a polynomial function, you ask? Right, what's a polynomial function? A polynomial function, you've seen a few. You've seen a linear graph, you've seen a linear curve, okay? So what's a linear curve? It's something of the form AX, okay? Then you've also seen a quadratic curve, and that's something of the form AX squared plus BX plus C. And you've also seen a function that looks like what's known as a cubic graph, AX cubed plus BX squared plus CX plus D. And over here, we've got C and D, all of these are the constants, right? So you could have AX plus B over there, okay? So what is a polynomial function, right? A polynomial function looks like this, and in more general terms, we would write it as it's a function of the form an x to the n, right, plus an minus 1, x to the n minus 1, plus, and so on, plus a1 x to the power of 1 plus a naught. Okay, now what in the world is all of that? Well, the an's, right, an minus 1, let's just put dot, dot, dot here in between, a1 and a naught, right? These are these things that you see over here, okay? And what are they? It's nothing fancy. This over here are coefficients, okay? They are coefficients. And these things over here are your variables in descending powers of x. So there I've got x squared, then I have x, then I have an invisible x here to the power of naught, right? Which is just 1. There's an x to the power of naught, so a naught will correspond to x to the power of naught. So again, don't be alarmed by this. This is just a general form of writing this to see that a polynomial is where I have some coefficient, a variable that defines that function, with descending or ascending powers. Right? If it's ascending powers, all that means is it's written back to front. Okay, so that's a polynomial function. Now, again, in general terms, if my polynomial is f of x, right? And again, that's the function notation, then, and it's written as a, and in this case, a is the coefficient, x is the variable to the power of n. Then I get the derivative, which is denoted as f prime of x. I'm going to go over certain things with regards to notation as well. Is written as n times a x to the power of n minus 1. Okay. Again, some of that looks abstract. Okay. So let's look at a few examples. Now, if I define a polynomial function to look like this, coefficient, variable, power, that's what makes a polynomial, right? And I say that the power rule is a shortcut for finding the derivative of a polynomial function. Then you must ensure before you apply the power rule, you have either a polynomial function or something that you can make it look like a polynomial function, because that will allow you to apply the power rule. Okay, so let's look at a few examples. Let's look at a few examples of differentiation with regards to the rules. Okay, let's take a few. Let's take simple ones. So if the function is given as 3x squared, so I take a function, f of x is equal to 3x squared minus 5x, right, plus 1. And remember, here's an invisible x to the power of naught here that I'm not going to write because you won't see it like that in an examination. But let's apply the power rule. And the question wants you to find f prime of x. And remember, f prime of x is the derivative, right? That's the derivative. So how do I find the derivative there? Remember, that's a 2. Now, applying this, the derivative says take the coefficient and multiply it by the exponent, or take the exponent and multiply it by the coefficient. So in this case, if that's my f of x, my f prime of x is going to be 3 times 2, which gives me 6. X And that n was the original power, but minus 1. So you take 1 away from the original power. So the original power was 2. You take 1 away, and you're going to get 1. Now, over here, 5x, you know there's an invisible 1 over there. If I take that 1 and I multiply it by negative 5, I'm going to get minus 5. I'm still left with my x, right? However, the power now is 1 minus 1. And anything, remember this, anything to the power of 0 is 1. So this whole thing is equivalent to 1. Now, if that's equivalent to 1, I don't need to write it in. Okay? I don't need to write it. And the constant term just falls away. And why does it fall away? I mean, we don't really want to drag that part out, but this has an invisible x to the power of 0. And 0 times 1 is just 0. And 0 times whatever is going to be over there is still going to be 0. Okay, so that's the answer over there. Let's do another question quickly. If I've got the function y is equal to 10x minus 4, okay, then I say that dy by dx, Imaad, what in the world is that? Where did that come from now? So remember the question over here is 10x minus 4. 10x minus 4, right? Let's neaten that up. The question is 10x minus 4. Now here, this is the derivative, right? Now I'm going to tell you something else. This is also the derivative. So I'm exposing you to different notations. When we use f of x, then the notation that goes with that for the derivative will be f prime of x. If I name the function y and I only use it as y is equal to something, then I say dy, the derivative of y, with respect to x, dy by dx. This here means the same thing as this, okay? What's that going to be? Well, that's just going to be 10, because that's 1 times 10. Okay, we got it? Gives me 10. Then I'm left with x to the power of 1 minus 1, which is x to the power of 0. That's actually the answer. But you know x to the power of 0 is just 1, so 10 times 1 gives me 10. Here, the constant term once again falls away. Okay, let's do another question quickly. Let's take x minus 3. Let's do it on this side. Y is equal to sorry guys, y is equal to, yeah, let's go back to doing something like this just to drill it in. One more like that, minus 3x to the power of 4 plus 4x squared minus 2x. Okay, so let's do that. Okay, let's add a constant term plus 7. Now, once again, you can see I've used the notation y. And if I use the notation y, then the derivative is dy by dx. I want you to pay attention to this and listen to how I read it as well. The derivative of y with respect to x. The derivative of the function y with respect to x. What's it going to be? Multiply. So 3 times minus 4 is minus 12. X to the power of 3. Right. 2 times 4 plus 8. X to the power of 1. There's a 1 there. 1 times minus 2, just minus 2. And the x to the power of 0, that falls away. The constant, the answer there is just 0. So there's my answer for the derivative. Okay. Now, the reason we could immediately apply the power rule over here is because we were sitting with a polynomial function. Now I want to give you a compounded function that is not a polynomial. And keep this rule in mind. Okay, keep the rule in mind. We take the power, we multiply by the coefficient, we minus 1 from that power. Let's take something a little bit more complex. Y is equal to, let's make it y is equal to x squared minus 3 over x. Okay, minus 3 over x. Now, oh my word, Imaad. What's going on here now? Oh man, that doesn't look like a polynomial. Because if it's a polynomial, it's got to have a coefficient, a variable, and a power. So what can I do? Well, try and turn it into something that looks like a polynomial, okay? So I'm going to leave it as y, and I'm going to manipulate the function, and we're going to put it into something that I like to call mimicked polynomial form. Right. So I want to have it look like a polynomial, even though it's not really a polynomial. Okay. So let's see, what's that going to be? So I'm going to leave it in this color. So I've got x squared. That's fine. I'm happy with that. But I'm going to change this to minus 3x to the power of minus 1. Okay. So now I'm going to go and apply the power rule. And once I find the derivative, look at my notation. These two things are equivalent. I don't write dy here. Some students write dy. And candidates, if you write dy here and you're not sitting with dy, it's not correct, right? In my class, we won't mark it right. I don't know what happens end of the year, but we definitely won't mark it right in class. So, okay, now I can find the derivative. 2 times what number's in front there? You know there's a 1. They taught you that in grade 7 and grade 8. So it's going to be 2 times 1 is going to be 2x. That number used to be 2. Now it's going to be 1. Okay. On this side, now we've got to be careful. I've got a power, and that power is minus 1. So minus 1 times the coefficient. The coefficient here is minus 3. So minus 1 times minus 3 will be positive 3x to the power of, I had minus 1. Take away 1, that's going to be minus 2. Okay, so what's that going to be? The answer then, that's the answer. That's the derivative. Now, sometimes the questions will ask you to put it in a form that has positive exponents. Then you simply change this to 2x plus 3 over x squared because you take it back to the denominator. But once again, if the question doesn't stipulate, write it in positive exponents, then you can stop over there and you'll get the full marks. Okay, so that's one example. Let's do one more quickly. Let's do one more. X minus 3, 2x plus 1. Right, so let's say I have a function, and I'm going to give you another notation now. Look at this notation, dx of, and I'm opening a bracket. Okay, x minus 3 into 2x plus 1. Okay, so ladies and gentlemen, Imaad, what the world is that? Guys, we're doing the same thing. We've just changed the notation a little bit. And what does this mean here? This over here means find the derivative. Another way of writing this is dx, open the bracket, of y. Now, if you put these two things together, look at the thing in the bracket and look at the thing in the bracket on this side. This is the same, that is the same. The bracket is the same, bracket is the same. Inside, I've got y, and inside over here, I've got something, okay? That's something that I'm looking at. That's something that I'm looking at over here and over there. There's an equal to sign in the middle. And since that and that is the same, this and this is the same, the brackets are all the same, indirectly over here, I'm trying to tell you that you're just sitting with a function written in the bracket. And this dx is another way of saying find the derivative. Okay, now how do we find the derivative? We're going to use the power rule. Can I use the power rule? Not exactly. What do I need? I need a polynomial function. Now, as it stands, this is a polynomial, but it's not really in polynomial form. So I need to turn it into that. Okay, so let's continue. We're going to find the derivative. So we're still looking for the derivative dx of whatever's in the bracket. So we multiply this out. That's going to give me 2x squared, right? That's going to give me minus 3, okay? And what is this on this side? I've got minus 6x plus x, right? Double check my working out, guys. Minus 6x plus x is minus 5x. So in other words, now the question, and this actually throws students off. Sometimes they come to the examination, they see dx of this bracket, and the examiner wrote equal to, and they're like, what am I supposed to do with that? Guys, it's just asking for the derivative, okay? Now, yeah, let's find the derivative. So now we remove the notation because we actually give the answer. So 2 times 2 is going to be 4. That's going to be x to the 2 minus 1, so it's just 4x. Here I've got an invisible 1, so 1 times minus 5 is just going to be minus 5. and it's x to the power of 0, which I don't need to write in, and the constant term falls away. And there's the answer for the derivative. Okay, so candidates, let's quickly speak about that notation matter that I had mentioned. Okay, we have about 10 minutes left. That notation matter. So if I am sitting with f of x, right, then the derivative will be f prime of x. If I'm using y, then the derivative will be dy by dx. Okay. Then the other two notations that you get, sometimes they have dx. This is actually asking you for the derivative. So you have dx of y. So they put the functional value of y in and you say equal to and you work it out. And then the other way to do it is where they have d by dx and they write the function here. But this is exactly the same thing as this. So another way to say d by dx of 3x squared plus 4x plus 1. Yeah, they're just asking you for the derivative of the function inside with respect to x. Okay. I hope you guys are with me so far. Yeah, this is regular classroom. We'd ask you to give us a thumbs up and pose any questions as we go along as well. Okay, candidates, the next important thing that I want to wrap up with on this is what in the world does this with respect to x mean? And I think we need to pull up maybe the 2019 question paper. And we need to talk about this because it's thrown kids off. It shouldn't throw you off because you're deriving with respect to a certain independent variable. What that means is anything that is not that variable is treated as a constant. That's what it means. Okay? So again, here the answer is going to be 6x plus 4, and we are done. Happy, excellent. Right. Now let's look at examples with respect to different variables. Right. Now, let's quickly just check November 2019 NSC Mathematics Paper 1. Let's just check that question paper. And I think, if I remember correctly, this question, there we go. Right, I'm going to pull it up, 7.2. Let's do both because what's nice about this is, there we go. Oops. What's nice about this question is this question, I didn't tackle a surd. So let's do 7.2 before we go to this whole story here. Okay. So if I go to 7.2, you must determine dy. So again, here's the appropriate notation that's used with this over here, if given that. Right. So now, this is not a polynomial because a polynomial is some number with, which is a coefficient, multiplied by a variable, and that variable raised to a certain power. Okay. Here, I don't have a coefficient. So I need to turn this into a polynomial form. So I'm going to rewrite the function and say it's y is equal to 4x to the power of 8. That part is definitely polynomial. Now in grade 11, you went over the surd laws, and you know how to rewrite this in terms of the surd laws. Remember, x to the power of p divided by q is equal to the q root of x to the power of p. Okay? So for this thing over here, I'm going to write that as x to the power of 3 over 2, because the square root of here is 2. Okay. Now I can say that this is in a mimicked polynomial form. It's not really a polynomial. Mimicked polynomial form. Okay. Now I can go find dy by dx. So now I say dy by dx is equal to 8 times 4, 8, 16, 32, right? X to the power of 7 plus, there's a 1 in front there, so 3 over 2 times the imaginary 1, that's going to be 3 over 2 x to the power of what? What is 3 over 2? You know 3 over 2 is 1.5. 1.5 minus 1 is a half. But 3 over 2 minus 2 over 2 is equal to 1 over 2. because we're minusing 1. Okay, so that answer there is 3 over 2 x to the power of a half. And we can leave it like that. We don't have to rewrite it and convert this back into a surd form because the question didn't stipulate in a surd form. Okay, so that is undoubtedly the derivative. Now, this question over here is really all about notation, candidates. When I say it's about notation, they give you a function. They ask you to determine dy by dx, which is equal to 2 times a times x to the power of 1, right? And nothing else, because this is like a constant. This is just a number, okay? Now, when we read this, we say determine the derivative of the function y with respect to x, meaning x is the independent variable. Any other thing that even looks like a variable means you treat it like a number, because this here, you treat it like a constant. This here is telling you what you are deriving with respect to. Now, if you go to the next question, and I want you to think about this and revisit this part of this video. The next question asks you dy by dA, dy by dA. So now you must take that same function and you must find its derivative, but you are deriving with respect to a. So in other words, a over here, that's the independent variable that I am concerned with, right? So I treat that as the variable, and anything else that is not that is a constant. So this here gets treated like a number. Okay. So if I find the derivative of that, well, that's a to the power of 1, right? And then this is in front of a to the power of 1. So that answer there is just x squared. Okay. And then here I've just got a, and there's an imaginary 1 there. So the coefficient of that is just x squared plus 1. And that's your derivative there. So really think about this. Maybe a person needs to do a few more examples. If I gave you an example, sorry, it's been a long day. Can't think of examples now, but we also are at 1 hour. Candidates, revisit the video, check this out. Remember what I've left you with. To sum it all up, we've tackled limits. We went over the plug and chug method, which is relevant when we have a continuous function. And it's perfect for anything that we will have in grade 12 because we don't deal with any fancy functions that are discontinuous, etc., etc. Okay, how do we deal with the plug and chug? We plug in, we substitute, we get one of 3 types. The 3 types that we get is either going to be an indeterminate form, that's 0 over 0, or we're going to get some number over 0, and that's undefined. Okay, or we're going to get an actual number. 0 over something is an actual number, or we get just a real number that pops out, and we can say the limit exists. Then we've covered differentiation from the rules. We looked at an example that involves a surd. We looked at an example that involves a fraction, right? And we also covered the notation. And then we defined what differentiation involves. It is about finding the gradient at a point, right? Or finding the derivative. And there's 2 ways to do so. One with first principles, meaning you use the definition, which is a long method that counts up to 4% in your examination paper, or you could use the rules, right? Now, there's multiple rules, quotient rule, chain rule, etc., etc., right? However, the only rule relevant for grade 12 is known as the power rule. And the power rule is used when we are finding the derivative of a polynomial function. Sometimes in grade 12, we have functions that are not polynomials, and we try and put them in a mimicked polynomial form. So candidates, thank you very much. We'll see you tomorrow. I think we'll be joined a little bit earlier. We'll confirm with the studio, and then we'll continue on this topic of calculus. We will be looking at first principles and also moving on to what is actually needed to sketch a cubic graph. Okay, thank you very much. It's been a wonderful evening, and I hand back to our brother Amir in the studio.
MashaAllah, we say shukran, jazakallah khair. And by terima kasih, thank you very much to Brother Imaad Isaacs for conducting today's session on calculus for paper one. And of course, from our side, from the Voice of the Cape, as well as I'm sure on behalf of Futures Academy, as led by Brother Imaad, we wish each and every one of our matriculants very well as you are preparing for your upcoming NSC examinations. May God Almighty Allah grant you all the success to tackle this examination period and to be successful in all of your endeavors coming forward. Of course, today was mathematics paper one, and inshallah, in the coming sessions, we will be tackling mathematics paper one as well as paper two, as well as the other subjects that we still need to tend to. On behalf of the Voice of the Cape, we wish each and every one of you, our beloved viewers, well. And inshallah, till we meet again, we say assalamu alaikum wa rahmatullah.